Hello all. Today we will discuss the intensity distribution due to single slit diffraction. As we know that in single slit diffraction, the intensity distribution on the screen is a result of superposition of waves that are coming from the planar wavefront which is located in the slit plane. As per Huygens principle, each and every point in the planar wavefront at the slit plane will act as a separate source of wave. To a first approximation, we can consider this wave as a spherically diverging wave. When this wave approaches towards the screen, when they reach the screen, they constructively and destructively overlap and gives rise to this diffraction pattern on the screen. So, from each and every point, rays of all angles will emerge towards the screen. But for the sake of simplification to our discussion, we are going to consider only two such rays. One ray which is emerging in perpendicular to the slit plane, that is this one, and another ray which is emerging at an angle of theta to the slit plane. So rays that are emerging perpendicular to the slit plane will be focused at a point P naught, that is at the center in the screen, and rays that are emerging at an angle of theta will go to P on the screen. Now here is the small portion of the above diagram. Here, instead of considering the full segment of planar wavefront, I am going to consider only a small portion of planar wavefront at the slit plane for our discussion. The width of this smaller segment of plane wave is ds, and it is located at a distance of s from the center of the slit O. Now we know this angle is theta, and if this angle is theta, then what is this angle? To understand this, consider this triangle. We know this line is drawn as a normal to this ray 2. So this angle is 90 degree. So if this angle is theta, then what is this angle? This must be 90 minus theta. If this is 90 minus theta and this is 90, then this angle must be 180 minus 90 degree minus theta plus 90 degree. So this will be theta. The displacement of a wave moving along the x direction and at a particular time t is used to express using the standard wave equation of this type. Now if I find the infinitesimal displacement at a point P for a wave that is propagated from the point O from an infinitesimal plane wavefront of width ds can be represented using this expression. So this infinitesimal displacement is directly proportional to the width of the plane wavefront that we consider and inversely proportional to the distance where we observe the plane displacement. And so if I shift the position of source in plane wavefront source, now I can represent its corresponding displacement by dy minus, and this beta is added since I remove the proportionality constant. So if I shift the source, there must be some path difference. So to account the path difference, I added the factor delta. Delta is the path difference. Now if in a similar way I can consider a plane wavefront element in the upper half of a slit, so which is dy plus is equal to beta time ds, the same factor, and the path difference this time would be subtracted. Now what is delta? Delta is the path difference which can be estimated. This is our delta. This is the path difference between these two rays. Okay, now the delta is nothing but s times sine theta. This is s and this is theta. So this side would be given by s times sine theta that I wrote here. Again, substituting this delta into equation 3 and 4, we can write the this displacement due to plane wave source placed in the upper and lower half of slit. It would be modified this way, and then finding the total displacement, we get this relation. It's addition of this and this factor, and this is common, and so this can be simplified using the trigonometry relation of this kind. Sine a plus sine b is equal to 2 times sine a plus b by 2 cos a minus b by 2. Applying this trigonometry relation for the displacement gives this expression. So for the full displacement, if I do the integration with respect to the slit with full slit width, I get this following integration, and so performing this integration gives this relation as this one, and adding and dividing by a give the final displacement in this form. If you see here, this part represents the progressive wave, whereas you can see here in this highlighted term there is no dependence of x and t time. So this is a constant quantity, and if I substitute this as amplitude, so I can write this in a simplified manner this way. Here a is nothing but this term, so which is amplitude of a progressive wave. So this amplitude you can see is a function of theta and position x. Taking this amplitude and finding substituting beta a by x as a naught and alpha is equal to ka by sin theta, give the simplified version of the amplitude in terms of a naught and sin alpha by alpha. So we know the intensity is directly proportional to mod a squared, mod of amplitude square. So doing that, we get I is equal to I naught sin alpha by alpha the whole square, where I naught is the square of a naught squared. So we know at the center of the screen P naught means at the point P naught our theta is equal to 0, and hence the sin alpha is a function of theta, that is 1. Sin of alpha in the low theta limit will goes like 1, means alpha by alpha will be 1, and we get intensity as I is equal to I naught, which is this I naught which is equal to beta a by x denote the central bright fringe. Using the intensity relation, one can find easily the directions of minima and maxima. First, let's find the directions of minima first. So, this is the intensity relation. I is equal to I naught into sine alpha by alpha the whole square. So, when the intensity will be 0, whenever this is equal to 0, this we know this is not equal to 0. This has to be equal to 0, then intensity will be 0. When this bracketed term will be 0, whenever sine of alpha by alpha is equal to 0. So when sine of alpha by alpha will be 0, whenever sine alpha is equal to 0. When sine alpha will be equal to 0, whenever alpha is equal to plus or minus m pi, then this term intensity will be equal to 0, and putting the value of alpha we get this relation, and cancelling these 2 and pi's we get a sin theta is equal to plus or minus m lambda, which is same exactly the same that we derived using different argument. If you can remember, in my previous video we have discussed how to get this relation or conditions for minima by breaking the slit into even numbers of interval, if you remember, and looking for the conditions of minima on the screen. Okay, that relation and this one both are exactly same. If you have any doubt, go back to that video and get it cleared. Okay, now looking for the conditions of maxima. So when my intensity will be maximum, whenever this derivative of intensity with respect to alpha is equal to 0, then the intensity is maximum. Okay, now taking the differentiation means d by d alpha is equal to I naught into sine of alpha by alpha the whole square, and I naught is constant if I take it out. So doing this in differentiation by u by v method gives the following expression: I naught sine squared alpha by alpha by 2 4, which further can be simplified to get tan alpha is equal to alpha. This is the conditions for maxima. So this equation is a transcendental equation. We don't know how to solve this equation. So this is one function, this is another function. So we have to look for value of alpha at which these two functions are equal. So this can be solved using graphically. There is no analytic method to solve this equation. Let's see. Here is the sketch of these two functions, tan alpha and alpha as a function of alpha. As we know, this alpha as a function of alpha will be a straight line, that is this line. And what is tan alpha function? We know tan alpha is a discontinuous function of alpha. So tan alpha can be written as sine alpha by cos alpha. Whenever alpha is equal to 0, sine 0 by 0, sine 0 by 1, we get 0. So whenever alpha is equal to 0, we get 0 or 2 pi. 2 pi, we get tan alpha as equal to 0. And whenever tan alpha is equal to Whenever alpha is equal to pi by 2, we get sine pi by 2 is 1, cos pi by 2 is 0, and this will go to infinity, and that is depicted here. You can see when alpha is equal to 0, tan alpha is equal to 0. When alpha is equal to pi by 2, it is tending to infinity. Again at pi, cos tan alpha is equal to sin pi is equal to 0, so the tan alpha function goes to 0, and at 3 pi by 2 again it goes to infinity. So it's an odd function also, on the negative side also it has to go. So the as I told, whenever the solutions are given by for values of alpha at which these two functions are equal. When these two functions are equal, whenever these two lines are crossing. Okay, here is the point where this alpha, tan alpha and alpha, they two are meeting. Again the meeting point is here, again the meeting point is here, again the meeting point is here. So here we have four such solution. So alpha is these are the solution, and these are the places where we get the intensity as maximum. You can see this is intensity as a function of alpha, intensity as a function of alpha. And since we have one solution here, intensity is maximum. Again the another solution is here, intensity is maximum. And again the another solution is here, again the intensity is maximum. So these maximas are happening at for values of alpha at alpha is equal to 0, 3 pi by 2, 5 pi by 2, 7 pi by 2. Okay, so in general this can be written using the following relation using m. Okay, if m is equal to 0, we get 3 pi by 2. If m is equal to 1, we get 5 pi by 2. So putting this condition means substituting the value of alpha pi a by sine theta by lambda, we get this relation, and cancelling this pi, we get a sine theta is equal to 2m plus 1 lambda by 2. This is the conditions for maxima in single slit diffraction. Okay, now substituting the alpha in the intensity relation, we get the ratios of intensity. This is the ratio of any orders of maximas with respect to the secondary maxima with respect to the central maxima. So if I substitute the value of m is equal to 1, if I substitute in this relation, putting here I am substituting the value of alpha. Now substitute m is equal to 1. That should give the ratio of secondary first order maxima with respect to the central maxima. So that is sine 3 pi by 2 divided by 3 pi by 2 the whole square, which is 0.045. So this relation is some sort of universal relation. Even if you do the experiment in some other planet like Mars and other Saturn, you will get the same ratio. Here there is no dependence of any physical quantity involves. Here you will get exactly the same ratios of intensity. Okay, now substituting the value for m is equal to 2, we get the second order in maxima, intensity of second order maxima with respect to the central maxima, that is 0.016, which is lesser than normalized first order intensity maxima, say first order maxima. Okay, now putting m is equal to 3 gives me the ratio of third order minima with respect to the central third order maxima with respect to the central maxima, which is further lesser than this value. So it will keep intensity keeps on decreasing when you go away from the central maximum. That's all. Thank you.